Yeah.
I think there'll be time at the end to have a
At that time, it's very much your decision and us is whatever it is.
As long as we watch it very closely so that we're not.
Absolutely.
There's a clock right there.
Yes.
For 25
Yeah.
and it drops down.
I
And
will not.
even otherwise, I'll show this in 5
Yes.
minutes.
The shot there. As long as you're not going to snap it.
No, no, it'll be like
It's
that.
gonna stab you in the side of the pin.
I could lend him my boot and just kick you.
And I think you gladly would want to do that.
No, I said I could lend him my boot.
No, I'm an expert.
Now you come in ruffling feathers.
I don't care either way.
That was being the oldest guy.
No, everybody's easy.
Yeah.
Regenesis.
Oh. My man, how are you? Oh, let me show you. Are you on
Biolargo.
anything?
Aqueous electrostatic concentration.
So you have to click it down.
So they're just gonna be on.
Okay.
So
Yeah, so don't say anything bad about presenters as they're on.
control the volume, but
Or at least point it the other way.
I've got reason to work with you. Wisconsin.
Wisconsin.
Yeah. I left 40 degrees and rain.
Well, and I live in the most beautiful place, Kansas City.
My daughter's roommate is actually from Kansas City.
UMKC, right?
What?
UMKC.
I actually went to KU.
Now, are you on the Kansas side or on the Missouri side? Okay. She's on the Missouri side.
Well, that's okay.
Because my daughter goes to school in Missouri. She was born in Italy.
Oh, yeah.
31.
I was just going to take some funny pictures. When are you going to let me do a 7-year-old workshop?
I went to Wichita State.
I do one in
Say that louder. You went to where? K-State?
Wichita State.
Wichita State. That's where you got your master's?
Yeah.
Oh, no.
And KU used to provide the Ph.D. degree for the graduates of Wichita State.
Yes, yes. And I think they still, well, in some specialties, in some things, yes. KU is a great school.
Chemistry, that's how it was.
KU is a great school.
I had a lot of friends there.
It's wonderful.
Like my professor did his postdoc at Okay, I think I'll start it.
Oh, don't worry, I can get the regular stuff.
We can cover it. No.
No, just alcohol.
Good afternoon, folks. Welcome to the PFAS assessment and remediation session. So we have 4 speakers on this panel and dealing with remediation technologies as well as regulatory update. So what I'm going to do is start off to provide some guidance on what you need to do for assessment from an analytical standpoint. And basically, when you start assessing for PFAS, you have to know what you have in your matrix. So in order to do that, to get a comprehensive understanding of the PFAS you have, you first start off with your regulatory methods, which is 1633 or 533 or 537.1, and then to add on to that because you don't measure everything in those methods. So you need to do a top assay to do the oxidation, so that way the precursors are oxidized to release the PFAS. And then on top of that, you need to do the non-target analytes, so you get a comprehensive analysis of what it is. And then the AOF method, which is the combustion IC method for measuring the total fluorine content. And then the other part of the method is we measure PFAS from C4 to C14. So you don't account for C1 to C3, which is a predominant player in the whole composition of PFAS you have in your matrix. So the C1 to C3s are called ultra-short PFAS. So I know there is no EPA method for top assay, non-targeted analysis, and ultra-shorts. So EPA is working on protocols for top assay, both in the drinking water matrices, as well as other matrices like wastewater, soils, fish tissue, all of that. But they don't have an official methodology yet. So you need to consider doing those in order to protect what you did from the beginning on the assessment. And the last part of it is, if you have PFAS foam and you're converting to non-PFAS foam, you need to make sure that you do the top assay on the non-PFAS foam, because you never know what is there by just analyzing by the AFFF foam method, because there could be precursors in it. You're not accounting for the PFAS. So it's always better at the beginning to do a comprehensive analysis to assess the PFAS. So that's what I'm going to say about analytical part. And our first presentation is going to be by Dr. Mohamed Odah. He's a principal at Accelerated Remediation Technologies. And he's going to talk about PFAS remediation in circulating wells, proven success, and confirmed efficacy. Welcome to Dr. Mohamed.
Thank you. Good afternoon, everyone. As you heard, I'm tasked to share with you remediation of PFAS in circulating wells technologies. What is a circulating well? Do we know what a circulating well is? And simply, it's a well, extract, treat, inject back in the subsurface. Nothing comes out other than vapors, and in PFAS, it is foam. Before I get in my speech, I just would like to say a couple of things. One, you will see me referring to circulating well technology one time and art technology another time. It's not my intention by any means to be a salesman. However, at this point, the only circulating well that I'm aware of that's been effectively proven in the market is the art circulating technology. So therefore, when I say the art technology or circulating well, I'm referring to the same thing at this point. With that, the technology, circulating well technology typically, as we said, extract, treat, and inject. You treat by different processes. You don't want to put one process at once. Combine different processes, because if you hang your hat on one process, you are risking it. So and there are several, more than one formation of one generation of the art technologies, depending on the contaminant, depending on what we deal with. So what I would like to do is I'm going to share with you the original design of the art technology, and then share with you some case studies and how it was developed to address different contaminants, including PFAS. But before we do that, what is the art technology in its original form? It combines several processes. We said in-well air stripping, underline in-well. In-well air sparging, underline in-well. Soil vapor extraction, bioxidization, depending on what the contaminant is, and dynamic subsurface circulation, as I'll explain that later. Add to that, we could always add amendments if it is needed. This is what a typical ART well looks like. You typically have a well that's 4-inch or larger, preferably 6 inches. Why? Because 6 inches give me the option of I could use different pumps. 4-inch well, I'm limited to with a 3-inch pump. That's the only difference. But if you have a 4-inch well, we can use it. If you have a 6-inch well, that'll be better. Notice that we have 2 separate screens. From now on, think of this as your extraction screen. Think of this as your injection screen. And the next thing is that you have air sparging, in-well air sparging. I'm not sending bubbles in the formation. It's done within the well. Why I'm not sending? Because somebody was talking earlier about the vapor intrusion issues. Well, this is my way to guarantee that I'm not pushing anything anywhere. It's done under my control, especially when you consider the salt vapor extraction above top of the well. So this well will always be under vacuum. The blower, the compressor are interlocked. If this goes down, this will go down. So this well will always be under vacuum. The next item is a pump, takes the water, sprays it near the top of the well, in essence, to allow the air that comes here to jet through it. Yes, I took the air stripping tower, I took the packer out, I put it inside the well. The air stripping concept, it's a wonderful concept. Unfortunately, in the past, it has always been associated with pump and treat. And we all know what happens when you pump tons and tons and tons of water to the surface. What we're doing here is we're taking advantage of it, but doing it in the well. And I'm going to like to make a note right here. PFAS, we don't want the PFAS to take us back to the pump and treat era. Those old-timers like myself are guilty of having put so many pump and treats in the systems in the past to discover later that was a lot of money was wasted. So please, whatever you do, do not go back to the pump and treat approaches. So what happens when you get the system in operation? You are actually, when you start the sparging, you are actually creating negative gradient toward the well. And when you have the pump takes the water, sprays it near the top of the well, you are sparging between the 2 screens. You're putting about 10 CFM of air. This is now acting as your packer. So a particle of water that's going to have here is going to have a hard time to go down. It's going to be much easier for it to go back in the formation to create this, and from that to create what we refer to as the flushing zone, or the sphere of influence, or the circulation zone. So again, think of it, this particle goes back in the formation, flushes, come back. Now remember, negative gradient, pressure. So in essence, I have a torque. There's negative gradient, there's pressure, so there is a torque. And anyone that claims he has a circulating well without showing you this torque actually does not have a circulation well. Now, because of that, the velocity of the water is much faster than the natural velocity in the subsurface. So as a result, you end up flushing a lot of the contaminants and bringing it back toward the well, and that's what causes your rebound potential. So by flushing it, you minimize or eliminate the potential of rebound. How far is this? This is the function of KV, KH differences. Rule of thumb for estimating it for your project, think of it as 3 times X. X being the water column right here. So if you have 10 feet, you should be able to affect 30 feet. Why do I say that? Because in nature, KV, KH differences will never be less than 1 to 3. Maybe 1 to 4, maybe 1 to 5, but 1 to 3, you're conservative enough. You can apply the technology in different ways. You can source treat, or like some folks were talking about this morning about controlling hydraulic control, what have you. In this case, you'll treat the water before it goes down a gradient without having to pump tons of water. Now, just quick scans of some case studies, and then we'll move into the next phase of this. And this is a actually service station, big truck stop in Atlanta, Georgia, and Saprolite Formation. They came to us. There was actually right here a creek, taking it in a recreational lake. Was a big concern, so they wanted something to take care of it very quickly. They came to us. All of the data I'm sharing with you, figures, they come from the consultant. I didn't touch that data, just so you know. So with this here, this is what we started with, 6 R12s. A year later, it took it down to this. Another year was below action level. This site was closed, and the closure level was accomplished. This site is in the area of Sao Paulo, Brazil. Major terminal there that a lot of different contaminants, VOCs, petroleum, 1,4-dioxane, major chemical company. They were actually, the consultant was tasked to pilot test 7 different technologies. ART was one of them, and the 3 R12s were the pilot study. To determine the risk of influence, you rely on several parameters. One of them is what happens to the concentration. Well, let's go back here. One of them is what happens to the concentrations. You look at the time zero concentrations and look at it with time. DO changes, vacuum influences, and ORP. And here, because of the high profile of the site and the nature, the pressure that was on them, they actually went to pressure transducer and went to dye testing. They put a dye in the R12, monitored for it in monitoring wells, another dye in monitoring wells, monitored for it in the R12s. And from there, and they did it with time, and they looked at mass removal. And from there, they determined it is the most effective technology. They went, implemented it several. So this is a huge site. So there were a lot of different areas of concern, and they went with time, and this site is closed and behind us. This one here is in New Jersey, 80 years of operation, more than 200 areas of concern. So I'm showing you some sites that typically you would have hoped to see some results in 50 years. But time has changed and technologies have changed. This site, in one of the areas, we implemented it by itself. Another area, we implemented it in conjunction with ozone. Another area, in conjunction with electrical resistance heating. So our technology is flexible. The circulating well technologies can be implemented along with different other technologies and by itself. Very flexible, very easy, tailored. Well, the results, 150 R12s at that site, 2 years of operation. After 2 years, closure activities started. Results was grand prize environmental sustainability from the American Academy was given to the consultant in behalf of his client. And 1,4-dioxane, again, sites closed, closure occurred. These are, this is a pilot study, and from there went to full implementation. Just so you know, we started in some areas at this site with 60,000 ppbs of 1,4-dioxane. Not the 500 ppbs or the 400 ppbs, 60,000. And this site was closed and a closure letter received, and it's behind us. Now, we come to the PFAS, and I see I have 14 minutes. Perfect timing. PFAS, see, when you treat and deal with a chemical, a contaminant, you look at the characteristics of that contaminant. For PCE, TCE, we use volatilization because it volatilizes. For other, 1,4-dioxane, we put ozone because it oxidizes. Well, what is the thing that has been proven to be a main characteristic of PFAS? It fractionates, it foams. That's why it's used in foam. So, and some, as you know, some started, fractionation has been with us since the 70s, has been established as a remedy for PFAS at that, and in the 70s. But we started really seeing it implemented in a pump and treat format recently. Said, why can't we do it in situ on the subsurface? And that's what we started. We look at the PFAS treatment in both ways, and actually at 2 fronts: the fractionation aspect, the volatilization, and this remains to be seen depending on, can we oxidize it? Can we buy it? The jury's still out. But for now, think of the fractionation and the volatilization. I guess it's a fact, it fractionates, i.e. it foams. Also, it is, so the idea here becomes experiment with how to optimize the fractionation, how to make it foam the maximum possible. And that's, we went to the lab, we did our own analysis, we, where do we pump? Do we, sparge? How much do we sparge? How deep do we sparge? What kind of sparging heads do we use? And so on. So we played with it quite adequately. Then from there, and one of the things, do we spray above the water? Do we spray below the water? These are things also we had to decide, and depends on the specific site and what have you. That's why we become, at every site, we become part of the team with the consultant. We work with the consultant. He knows about the site, we know about the remedy, we combine our knowledge, and that's how we get to it. And as far as the volatilization aspect, I'm not making science. There's our studies here confirming that there is some significant volatilization that will occur. So between the fractionation and the volatilization, let's go and do our demonstration. Demonstration, when I say demo, we're referring to installing it in the field, running it for 90 days, and seeing what happened. And from there, we went, this is an actual an operating well, at a site in New Jersey, and you could see the fractionation, the foaming. So there's constant pumping, extraction of the, not pumping, extraction of this foam. And 9 wells at this particular site. 9 ART wells. This is the groundwater, is about 25 feet down. I think it's more of a, the hydraulic conduct about 10 to minus 4 centimeters per second. And the results actually more clear. This is the concentrate that was extracted from the ART well. No, actually, this is the ART well itself. The reduction was 90 to 99% within the ART well, within the treatment well. So that means 3,000, we were actually down to less than 30 within the ART wells. What does that tell us? That tell us, and this is in how long? In 2 months. That tell us that achieving action levels is not an impossibility as we used to think. Well, look at, this is the this is the PFAS enrichment in the foam. Look at the concentrations in the subsurface. You look at the concentrations in the foam. It's 5 to 100 times the concentrations in the foam. You also look at the monitoring wells. Up to 40% in monitoring wells, these are wells distant from the ART well, in 8 weeks, in 2 months. In addition, if you look at the water, this is the water samples and the tank. Now, keep in mind, folks, all of these analyses come to me from the consultant. It's not stuff that I made. The consultant provided this data. So I actually took this presentation, the slides from a presentation that he made to the agency. So this is, you see the concentration. If you look at the, see this 50 gallons. And see this 500,000 gallons. This is the amount of water that was circulated, 500 gallons. We recovered 50 gallons of foam, meaning that you would have had to pump and treat on the surface 500,000 gallons to recover the 50 gallons in foam or of foam that way. So you saved yourself the trouble of having to deal with 500,000 gallons of water on the surface. Translate that to NPDES permitting and costs and sampling and this and that. Now, the last thing I want to share with you very quickly is based on that, and I have time, based on that we went and we actually enlarged that to something that we all know is coming. POTWs are showing some serious concern right now about accepting leachate, landfill leachate, that has PFAS in it. So now, very soon, you will need to be treating the leachate from your landfill somewhere, somehow. Well, this is the leachate cell that we've developed to using the same approach, the same design, but it sits within the leachate stream to treat it, minimize the PFAS before it goes out of your reach and before it goes into the POW. This is what a typical art well looks like, my friend. We're not talking about major structures here and massive construction. This is a 2 by 2, 2.5 by 2.5. And if you don't even, if you're in a grass area, you don't have to, you don't have to put in a manhole. You could even finish it above grade. And if you don't want to look at it, get this fake rock and put it on top of it, and you'll be in good shape. So this is actually, I'm doing very well, actually. This is actually the end of the story here, and I'll be happy to take any of your questions, but please, out of mercy for the old man ears, speak louder so I could hear you if you have any question. Yes.
Together, I mean, you're basically vacuuming the foam as it comes to the top. Is that right?
Yes, sir. The foam, the fractionation product, the foaming is actually extracted constantly out of the well. And we use the vapor extraction system, just some modifications, use the system to extract the foam and put it in a tank, in a knockout drum tank before it gets to the system. Yes, sir. When actually you get it and it's foam and give it time and it's now liquid.
Okay, it will
reduce down significantly. And by the way, I was actually chatting with some, there are some studies, some efforts right now to create something or to use that foam in manufacturing some kind of chemicals. I've got a call from someone that actually wanted to take some free because it's being proud, but if that happens, then we actually, that's going to make a big difference because that foam is actually going to go into producing something good, something usable. Yes, ma'am.
Hi. At the site in New Jersey where you have PFAS and you're foaming it and extracting the foam, are you also treating the vapor that you are extracting from the well? Because there might be aerosols on top of which this PFAS is stuck. So do you have a carbon for treatment on the vapor side?
Yes, ma'am. Actually, the vapor extraction, because at this site, and like it's going to be most of your sites, it's highly unlikely that you're dealing with PFAS by itself and only PFAS. Most likely you're dealing along with it with other, chlorinated compounds or something else. So yes, you're extracting it, and there's going to have to be a carbon canister or something, or some kind of treatment for but luckily that's the business of the consultant I'm working with. He makes the big money, so therefore he gets to deal with that. But I'll be happy to advise him on what I think is the right thing to do at that circumstances.
Thank you. You mentioned that you allow for the foam to stabilize in the knockout tank. Do you rotate knockout tanks, or do you shut off the system for a period of time to allow the foam to attenuate and then remove it from the knockout tank?
I hate to admit this, but I did not get it. Did anybody get the question?
Yes. Do you, when you're pulling the foam off, is it a constant, or do you change out your foam tanks to allow the foam to settle?
Well, as soon, on the knockout drum tank, there will be some, some alarms to let the consultant know that this is getting full, and he's measuring based on the liquid, what have you. But I assume that there is a way to determine if the foam, if you get into a point where it's time to pump out. Now, there are actually, most of these knockout drum tanks, they have an auto pump on them. That auto pump takes the whatever liquid that's collected into a larger tank.
Not really, yeah. Basically, what I'm asking for is a holding time in the knockout tank to either shut off the well or the system temporarily on a timer, or do you rotate the knockout tanks?
Again, honestly, I don't have the answer for that, what the consultant is doing at that site. But I'm not, from the system design I saw, or I looked at, he does not, I don't think he's rotating tanks.
Okay. So is he on a timer?
I'm sorry?
Is he on a timer where he temporarily shuts down the well or the system to allow the foam to turn into a liquid so it could be extracted from the knockout tank?
Again, I'm not sure if he has a timer on it. I know he sends someone to check that system, like once a week or something, but I'm not sure if he has a timer.
If you don't know, you don't know. That's fine.
Appreciate it. Faiz.
Nice presentation, Mohamed. So I have one question. How do you dial in your airflow rate so that you're optimizing the fractionation as well as stripping of the CVOCs or any of the other VOCs that you have in the mix?
Those are serious design questions, Faiz. Depending, like I said, we become part of the design team. Like I said, the consultant knows all about his site. We know about the technology. We want success at the site. So we look at the site. We look at the other contaminants. And with that other contaminants, if you have high enough, if you have DNAPL, for instance, something, the approach is going to be different. So every site, the design for every site is going to be different from that. It's not like a one size fits all. So, but as far as where, and if it's only PFAS, we would like to spray below the water table. If there are other contaminants, we'll spray above the water table and adjust other things. And now there are two top secret stuff that I have to stop at. All right, thank you.
Thank you, Dr. Mohamed. And thank you, folks. And if you have further questions, Dr. Mohamed has a booth in the exhibit hall, so you can have discussions with him. So our next presentation is in situ remediation with colloidal activated carbon to reduce PFAS risk and liability. And it's being presented by Brett Hicks, Central Regional Manager for REGENESIS. Please welcome Brett.
All right. Well, thank you all first and foremost for taking time out of your day. My name is Brett Hicks. I'm the Central Regional Manager for REGENESIS. I reside in the state of Indiana, cover basically from North Dakota down to Florida. So pretty large territory. Got several folks with me out at our booth that help cover that territory. Yeah, I'll go ahead and jump right into it. As mentioned, I'm going to discuss the in situ remediation of PFAS utilizing colloidal activated carbon and kind of the process that we go through in utilizing this process. First and foremost, I'm going to step through the challenges of a PFAS project and some of the issues that we often have to deal with and overcome on some of these sites, some of the misconceptions with conventional approaches that's been utilized, pump and treat primarily, get into the risk perspective and how we're eliminating risk and reducing the exposure risk. And then wrapping it up with introduction into colloidal activated carbon, kind of what it is, how it works, and how we're utilizing it. But first and foremost, just by a show of hands, I kind of want to get an idea of the experience in the room with who in the room is actively working on PFAS sites. Just a show of hands is fine. All right, so yeah, a good, probably 50% are actively working. That's great. As I mentioned, I work across a pretty large area of the country, so it's interesting to see the different areas of the country and how different parts of the country are approaching PFAS and who's working on it and who's kind of taking the wait and see approach. Starting with the challenges of PFAS. Obviously, PFAS are very resistant to degradation, right? They get that name, the forever chemical. Honestly, they're very recalcitrant in the environment. They're tough to get rid of. They're found everywhere. We're starting to see them in the Arctic, done studies on polar bears, finding them in polar bear blood. So everywhere we're looking for them, we're finding them. The PFAS fate and transport, that's a challenge to overcome. When we're looking at, a traditional CVOC, those fate and transports are very well understood, but the PFAS, we're still starting to wrap our head around how they're getting into the environment and how they behave once they're in the environment. So a lot of challenges there. And then you tag it with the lowest cleanup criteria of any COCs that I've had to deal with. In those low PPT levels, we've never had to achieve those low levels. So put all those things together, it's a real challenge on our hands. And currently, and what I'm going to get into here today, we've really got two available approaches that we're attacking these challenges. The pump and treat, bringing the contamination to the surface and treating it on the surface in various ways, foam fractionation, carbon vessels, different ways of actually treating the contamination on the surface and then doing something with that. And then the second being in situ remediation. And treating that in the subsurface, and I'll focus on the immobilization of PFAS within the aquifer here today. I'm going to start with the pump and treat side of things, and because that's kind of what we all know, and that's what's been utilized so far primarily. Starting to ask ourselves, how is pump and treat going to be effective in flushing these aquifers of the contaminants? Kind of as Mohamed touched on earlier. It's been shown after decades we've utilized pump and treat. They certainly have their place in some remedial strategies, but where they really struggle is achieving those relatively low levels of PPB goals that are oftentimes targeted for a chlorinated solvent, and they're just not effective in that realm. So, when we look at a PFAS, and they're traditionally about 25 times more absorbent in the matrix, much more difficult to get out of the ground to pump to the surface in the first place. Then we pair that with the PFAS standard of 4 parts per trillion. That's going to be really difficult for a traditional pump and treat system to effectively be able to mitigate and treat. Summarizing, it will likely take about 100 years, hundreds of years, for that water to be flowed through and be able to effectively mitigate that subsurface PFAS contamination, if ever. It's a continuous source. You're gonna be pumping for a long time. Mohamed touched on the high number of gallons, thousands of gallons that you're going to be addressing, bringing that to the surface. Then we introduce the risk of that PFAS exposure and the liability with the CERCLA designation once we bring it to the surface. That's not a new concept, right? We've had to deal with that as bringing hazardous substance to the surface, but PFAS is a little bit different, right? It's not being degraded. So no matter what we do when we bring that to the surface, we transport it to a new facility, whether it's a thermal treatment facility, a RCRA landfill facility. That liability is cradle to grave. So once that waste leaves your facility, you're still attached to it, maybe a month down the road, maybe 25 years down the road, but that's a challenge that you're going to have to bear sometime down the road. Whereas a colloidal activated carbon or an in situ approach, we're not taking that risk out of the ground. That risk is staying on your site, and the liability will remain there. So, moving into the meat and potatoes of this presentation and focusing on the in situ part of this remediation and the colloidal activated carbon application, I want to start with taking a look at the ITRC's definition of remediation here. I'm just going to read this aloud. Remediation is a process used to reduce or eliminate the risk for humans and the environment that may result from exposure to harmful chemicals. This is something we've utilized for a long time. Think about the way we've done 1,4-dioxane, some of these metals. It's a risk mitigation strategy, is an effective remedial approach. So what is risk? Everybody saw this, this equation. Got a hazard times the exposure equals risk. So if we're able to eliminate one of those components, whether it's we eliminate the hazard or we eliminate the exposure, we can eliminate the risk. In our case here, we're trying to eliminate the exposure on site in situ to eliminate the PFAS risk. So introducing everybody to colloidal activated carbon and kind of what it is. Does anybody have familiar experience with colloidal activated carbon? Has anybody utilized colloidal activated carbon? All right, great. A couple of you. So colloidal activated carbon is a form of activated carbon, just like we've utilized for many years in a pump and treat system, but we've milled that particle size down to 1 to 2 micrometers, about the size of a red blood cell, so very, very small. And it's suspended in a colloid, an organic polymer that aids in a wide distribution within the subsurface under very low pressures, allows us to take advantage of a very large amount of surface area for fast absorption, to be able to lock up those PFAS and chlorinated solvents, petroleum, hydrocarbons very, very rapidly. So what is a remedial colloid? So a colloid is a mixture of particles that stay in suspension without limited agitation. As you can see here, think about like paints and milks. Those are a couple examples of a colloid. The beaker there on the left is a stabilized microscale activated carbon that is suspended in the organic polymer with a destabilized microscale activated carbon on the right. Same carbon, just the lack of the polymer. And you can see that the distribution stays in suspension much easier. There's no agitation needed, and that aids in that distribution within the subsurface. Just a couple videos here. Hopefully they'll work. I always wonder if they're actually going to play. But you can see the beaker of colloidal activated carbon just being injected into that beaker of water, how easily it balloons and distributes within that beaker. The next video here is colloidal activated carbon, the sand column on the left being gravity fed from the surface. As you can see, it adequately distributes from top to bottom without the introduction of pressure of any kind to be able to distribute that carbon. Powdered activated carbon on the right, you can see it's not able to move through that same sand column without the activation of pressure, right? The carbon particles are just too large for it to be able to fit through there. Getting into the actual efficacy of the PFAS. So this is one of our longest standing PFAS projects. It's a site in Michigan, Camp Grayling. If anybody's familiar with that particular project. But this is a pilot test that we're going on 5 years of data. You can see the plume stop barrier indicated there on the left. The blue line is our upgradient PFAS performance monitoring wells, indicating the amount of PFAS coming into our barrier. Then the green is indicated our down gradient wells measured. You can see the PFAS, nothing's been done in the source area, so our PFAS concentrations have remained pretty consistent with a little bit of uptick here recently. But the PFAS down gradient wells have remained non-detect or very close to it since very rapidly post-application within 30 days. And we're right at 5 years of application data to show that. Now, you will see down here on the bottom, as the PFAS regulations and everything has kind of progressed, we've kind of had the moving goalposts, right? We've all had to adjust accordingly. So we were, this was targeting a 70 parts per trillion was our goal to start with. We've been able to stay below that in that 10 down to 2 parts per trillion since the application has been completed. But how is colloidal activated carbon different than granular activated carbon? I know I mentioned earlier that it has a lot to do with the surface area and the overall size of the particle, but there's a lot to that. So the smaller area, smaller particle size really allows those contaminants to work within and inside those carbon particles and utilize the full extent of that carbon. It's much more effective, much more longer lifespan from a carbon perspective, and much more rapid absorption that occurs in the smaller particle size. And you can see on the graph on the right here, it's just a series of different sized carbon particles going from 500 micrometers in the purple all the way down to the less than 53 micrometers in the red. And you can just see how much faster and able to maintain that, the smaller the particles as you go. This kind of just illustrates the same thing, but shows the two different particle sizes. But the key takeaway there, you know, if just giving the very low amount of time that the contaminants are coming in contact with the carbon, the small particle size is much more effective. And that's why we see in a traditional pump and treat system utilizing granule activated carbon, we see those the carbon vessels fill up so fast. It's the residence time just doesn't allow that contamination enough time to migrate into the cores of those carbon particles. The effectiveness and longevity, we've done some third-party evaluations on this. This is a QR code for a remediation journal document evaluating the longevity of colloidal activated carbon. Took a look at 17 field application sites where colloidal activated carbon was applied. Oftentimes it's a commingled plume. We're rarely dealing with just a PFAS contamination. We're dealing with chlorinated solvents or hydrocarbon plumes commingled with the PFAS contamination. So we do have to take into account those competing factors when we're looking at a colloidal activated carbon approach. Modeling indicates on this third-party evaluation that decades-long treatment will be effective with a single application. Short-chain PFAS will absorb to a small degree. They're a little more difficult, but they will be handled with a colloidal activated carbon application. The longer chain, which is oftentimes our risk drivers, are extremely good and absorb very, very well to a colloidal activated carbon application. What are possible limitations? All effective remedies, they have a range, right? We haven't been able to find that silver bullet of one thing that works well everywhere. Colloidal activated carbon is no different. You know, plumes where we've got these hydrophobic competitors, think of BOD and landfill leachate, is certainly a challenge. Very fast moving plumes, clean aquifers where we've got just a very fast aquifer scenario. The very deep plumes, the colloidal carbon will still work in these very deep plumes, but you know, oftentimes the application is cost prohibitive in those scenarios. Not to say that colloidal activated carbon approach will not work in these. It's just something that we have to take into account and make sure that we fully understand that conceptual site model on those type of applications. And we do that by utilizing a in-house model that we've developed called Plume Force that allows us to help aid in these designs and to account for those high contaminant flux zones, be able to take that, incorporate that into our design model, as well as the competitive absorption, other contaminants, natural organics. We can account for that, and then we can actually model the lifespan of these colloidal activated carbon approaches and show, hey, this particular setup, we're proposing maybe a 10-year lifespan or a 15-year lifespan. Client may say we only need this to last 5 years. We can model it as such, utilizing our in-house Plume Force model. Pretty powerful. As we just mentioned, the expected longevity, assuming a constant incoming flux of PFAS, nothing being done with the source. We've estimated decades long performance longevity, 50 to 75 years with nothing being done in the source. A reinjection would start that clock over if we do start to see some breakthrough, because there is no degradation occurring in there. So if that carbon does fill up faster than we would have anticipated, a simple reapplication in situ would start that clock over. But what if we treat the source? We eliminate that influx of PFAS coming into the system. That's really going to enhance that downgradient longevity, obviously, and the likelihood of needing a second application is very, very minimal. So targeting the PFAS sources, there's several ways that we've been able to do that, and going in and stabilizing the PFAS absorb to the soil, hitting it at the heart of the source area, eliminating that leachability, targeting the air-to-water interface down there at that capillary fringe, locking up that PFAS within that capillary fringe zone, and eliminating that continued treatment into that dissolve phase system. So in order to do that, we have a couple different formulations of colloidal activated carbon for the source zone treatment. Being able to reduce that leachability of soil contamination is extremely important, holding that migration of the PFAS in the groundwater. As I mentioned, it's in two formulations. There's a liquid form as well as a solid form for an excavation application. Distribution is key, just as we're dealing with a subsurface distribution on the soil mixing side of things in an excavation. Think about an ISCO. Contact is key. We've got to get that contaminant in contact with the carbon in order for us to be able to treat that. Colloidal activated carbon released once it comes in contact with the moisture within that subsurface, whether it's natural moisture in the soil matrix or it's introduced in a excavation with just adding water, enhances that distribution, allows the colloidal activated carbon to penetrate deep and coat those soils, especially important when we're talking about silty and clay type soils. Very rapid results, similar with the groundwater approach. Once it comes in contact with those contaminants, it grabs a hold and doesn't let go. Got just a few field application slides showing our field application here. You can see this was done with our R&D facility, just a simple excavator bucket mixing in, and the picture there on the bottom is just showing that carbon distribution, getting full coverage within our source treatment area. The next slide is a site we did in Alaska, very similar approach. And the stark contrast between the two, obviously you can see the carbon coated on the left and the uncoated particles there on the right. There's no question on where your distribution is and where you still need to treat. So, it's a good indicator of distribution. And here's an actual case study utilizing the source treatment back to the Camp Grayling facility in Michigan. We started with the plume, as I showed earlier in the presentation, but then we went back up to treat the source. Same thing, went in with a little more sophisticated mixing apparatus on this one. Did use the soil mixing head, mixing the solid carbon activated particles into that subsurface. You can see here we're starting north of 1,000 nanograms per liter in the soil here. Post-treatment, we're beyond a year at this point, still holding at 99%, greater than 99% total PFAS reduction within the leachability of that source zone. So, in summary, benefits of a combined treatment, as I mentioned, the longevity of a traditional PRB is going to be long-lasting, upwards of 50 years. But when you're able to combine that with source treatment, cut the head off this thing, it's really going to immensely impact the longevity and less strain on the downgradient PRB. And we're protecting those downgradient receptors. The PFAS plume is no longer migrating off-site. And one thing I do want to just mention here, this is all the program done within REGENESIS utilizing the colloidal activated carbon is warranty available. We do provide a guarantee that this will perform as designed. So what is the cost? Everybody always wants to know the cost. Pick it up here. So I have two very small sites opposite ends of the spectrum. We've got a small industrial site here we did in northern Canada, $73,000, very small pilot test. It was a commingled petroleum plume. The estimated pump and treat for that same exact pilot test project was $1.35 million. So you can see the overall savings there. On the opposite end of the spectrum, this is a large refinery project in Michigan. We implemented a full-scale plume stop application on the scale of $3.5 million with the estimated pump and treat side of 20+ million. So two very drastic sides of the spectrum, but overall, it's about 1/3 of the cost of a traditional pump and treat system for a traditional colloidal activated carbon in situ approach. Social environmental impact. This one's big, you know, here in the kind of what we've got going on here, especially down in y'all's neck of the woods with the hurricanes going on. But we got, you know, a drastic greenhouse reduction in greenhouse gas emissions, a much smaller footprint, carbon footprint, but it's highly resilient to hurricanes, natural disaster type things. There's no infrastructure from an in situ approach. If electricity goes down, anything like that, there's no operation and maintenance. The colloidal carbon's just down there doing its thing, and it's going to continue to do it no matter what's happening on the surface. So pretty resilient, pretty important, especially as we're seeing the times where we are. No contamination brought to the surface. We're not spreading that risk, as I mentioned earlier. That liability stays on the site. No waste is created. The PFAS sites that we've looked at, so we've got about, that number's pushing 70 sites now, so we keep increasing that every day across the globe. Obviously, we've got most of them here in the U.S., but we do have several sites over in Europe. They're, I would say, a little bit further ahead of us, but we've got a wide breadth of sites across the globe to pull from, so a lot of experience from a PFAS standpoint there. Wrapping this up, I've got a proven method utilizing colloidal activated carbon to achieve these very low standards that we're going to be forced to hold to here. No PFAS waste being generated, no lingering exposure risk, very low cost when compared to a traditional pump and treat system, and we can do that all with a warranty performance guarantee in the long run. So yeah, with that, I'll take questions. So I can hand you, I got one here.
I have 2 questions.
Sure.
Is it on? Okay. Hi, so I have 2 questions. The first one is related to the soil mixing project that you were talking about. And so it started off with PFAS at a certain concentration, and then it had progressively gone down from there. And it's not a question of the technology, how it works, but it's more how are you collecting those samples and analyzing them? Because if you're collecting soil samples that are also mixed with the colloidal carbon, how are you separating the soil from the carbon in your analytical testing?
So how, I'm not sure I understand the question, but
because the soil's mixed with the carbon, and so when you pull a soil sample,
it's
out of
covered
that,
in carbon. Yeah, the carbon goes with it, and they will analyze that in the lab with the carbon. Once it's mixed in there, it becomes part of the matrix.
And so I guess I'm just trying to figure out how you know that the PFAS is no longer in the soil if you're also analyzing carbon?
So it's just eliminating the leachability. It's not coming off the soil, so the carbon's holding on to it. It's not degrading it, so it's still there, but it's just no longer available to leach from that soil.
Okay. And then I just had one second question. Do you observe in practice conditions in an aquifer where PFAS or other chemicals are desorbing from the carbon?
No, not under normal circumstances. Now, we can see a carbon barrier fill up, you know, really understanding the mass flux, how much contamination is there and how fast is it coming to our barrier. But once it's absorbed to that carbon, we do not see it be kicked off, if you will. Thank you, ma'am.
Anyone else?
Over here.
Appreciate your talk. I have a question about when you're doing an application and then you inject the colloidal carbon, and I know there can be issues with that colloidal carbon staying in solution and suspension for a long time, and I know there's different discussions going on about how to park that carbon and to get it to do that. Have you had any pushback or have you had any consensus from regulatory agencies of when you can actually sample that groundwater and have that carbon removed from it, so you're getting an actual representative sample of PFAS still in solution rather than combined with the colloidal carbons still in suspension?
Sure, it's a great question. And it varies by state. And I wouldn't say we have any pushback on when. Our standard sampling procedure for when you can sample, and that's not necessarily PFAS related, but any colloidal carbon application, we want to be able to let that carbon set up, and typically that's going to happen within 30 days, typically. Sometimes it takes a little longer. Our general rule of thumb was we'll collect the groundwater sample, and as if you can see through the beaker or the 40 mil VOA, if it's gray in color, but you can still see through it, you can sample it. But that's about it. I mean, it can still be sampled, but to your point, we can park it using different technologies to be able to immediately pull that carbon out of suspension and park it in place and treat it that way. Anything else? Yes, sir.
Correct me if I misunderstood, but the way I understand the application, you're gonna capture it with the carbon. It's in the subsurface. Every once in a while, we have to go back to it. For how long? Is it for the rest of time? Is it when do you call it, okay, we're done with this site, we go somewhere else?
So that timeline, obviously I don't have 50 years of data to be able to support that. But we've had a couple third-party reviews that have done a look at that longevity, and it's anticipated to hold for 50 years before a second application would be necessary. So nothing would be done for many, many years once it's in place.
Okay. I think we are
Thank
out
you.
of time, and thank you, Brett. Appreciate it. The next presentation is a pilot study for the Aqueous Electrostatic Concentrator, an efficient low-waste solution for PFAS treatment in water. This being presented by Ms. Tanya Chandler. She's the president of BioLargo Equipment Solutions and Technology. Please welcome Ms. Tanya.
Thank you guys for sitting through many, many presentations on PFAS. I know it can be mind-numbing, especially since we're sitting here talking about a chemical that was caused by a laboratory accident over 70 years ago. And now it's in everything. You could actually say that PFAS changed the course of history, because if you know the history of PFAS, you'll know that without it, we wouldn't have had Oppenheimer's atomic bomb. It was the only thing that they found that would hold up to the seals for the uranium and the plutonium. But now we're getting to deal with the fallout. So my job at BioLargo, I'm president of the Environmental Equipment Division. And I eat, sleep, and breathe PFAS every day, literally. And we had a technology that was developed because we answered a call in 2017 when the EPA said we need to find ways to take PFAS out of water. Our engineers got together and they literally went to lunch and scribbled it on the back of a napkin. We had looked at a different technology that we had and realized we couldn't use that technology because that technology had received other grants. So they went, well, let's start at, right at the drawing board. And they literally did at lunch. If you know my engineers, it was probably sitting at the local Mexican restaurant over some nachos. The initial idea for this is that we were going to create a technology that had an anode and a cathode, and there were going to be membranes separating the process. And we were going to create a concentrated stream of PFAS in that anodic chamber, because PFAS goes towards the anode. So they put it together, and that's not what happened. What happened was we played Where's Waldo with the PFAS because we didn't get a concentrated stream of PFAS. And I'm going to go through this really quick, and I apologize because this is really high level. 25 minutes is not enough time to talk about PFAS. So in our system, what we found was that we didn't have PFAS in that concentrated chamber. That anodic chamber had no PFAS, but it wasn't in the main chamber of the system either. So we're like, where did it go? And then somebody started thinking about it. Did it absorb onto that membrane? So we actually had, when we started doing our FATE studies, we actually had to dissolve the membrane to find the PFAS, and that's exactly where it went. When we did our mass balances, we found out that in the process, as the water comes in, it literally binds to that membrane, and we can't get it off. We are able to wash that membrane. We are able to go exorbitant amount of hours on that membrane. Those membranes will last 1 to 3 years. And all of the PFAS binds to it. Doesn't matter if it's long chain, doesn't matter if it's short chain. And we've started our testing with ultra shorts, and we're getting the ultra shorts out. Because as PFAS migrate in, you've got an electrolytic field that's enhancing that draw towards that anodic chamber, but it gets stopped by that membrane. As you all know, PFAS stick to PFAS. So as you start treating, more PFAS and more PFAS, and if you would look at PFAS on a membrane under an electron microscope, what you would see is these beautiful little caterpillars of PFAS that form. And it's actually quite beautiful. Okay, I just admitted I'm a water geek. So, when we started doing our testing, we do use 537.1, 533, 1633. What I show you up here is primarily going to be just the contaminants of concern right now by the EPA, because if I didn't, all of my charts and graphs would need like 3 slides. So this is work that we actually did on groundwater. Now, the New Mexico study was the most brackish water in the United States. I can't tell you where that is, but if you're a government agency, you'll probably figure it out. We tested that water with the goal of getting it below 5 parts per trillion, because at the time when we ran this, the actual goal was 70 parts per trillion. And they wanted to get, they thought, well, no, nobody's gonna get it down below 5 parts per trillion, so let's set that as our goal. We ran this water later and took it down to 0. The second water I'm gonna focus on is the Kansas pilot that we did. And this is unique because this is a plume that's on the outside of an Air Force base. So this water not only was contaminated with lots of PFAS that you don't normally see, but this was also contaminated with TCE. And we did not actually have to remove the TCE to get the PFAS out. So we didn't have to airstrip it or anything like that. We were just able to take and run it through our system. So just to give you a bigger blow up of those numbers. We did actually, again, take that Kansas water down below these numbers as well. But their goal was 70 parts per trillion. They just wanted to hit that 70 mark, and we were able to get everything down. In the New Mexico case study, we ran across a few other PFAS that we hadn't encountered before, and you'll see we took them out very effectively. When you see the residence time in our system, that is the number of membrane serpentines that it has to go through. So when we say 5, it's going through a series of 5 membranes. And what you see there is that we were able to get almost everything down to non-detect. Now that whole process took less than 30 seconds. So this is really designed to be a part of that pump and treat that you guys are frowning on, but we all know at some point in time we have to take water out of the ground. If we didn't take it out of the ground, we'd never get to drink it. So at some point in time it's got to come out, and then there's points where we have to treat it. So this is one of the ways that you can treat it without creating mountains of carbon. Kansas, again, we encountered lots of different new PFAS. that we hadn't before, and including 6.2 FTS. What we found with our system is, like everybody else's, long chains come out really well. But we also noticed that short chains come out really well. And we hit the ultra shorts, and we've been able to pull those out too. They just take a little bit more time. So this is some of our removal efficiencies. Another case study for you as we're looking through this. This one is actually going into a full-scale commercial system. So this was a drinking water system for a small community system in New Jersey. What we have found with this system is that it works on water, groundwater, works on RO concentrate. So things, if you've got high salinity, it doesn't bother this system. So we've been able to actually do some case studies where we're running on high salinity and high chlorides. We ran the Wisconsin case study, and one of the things that they asked us to do is, could we tailor the chlorides coming out the backside of the system? If you're separating things and you've got ions going either direction, can you tailor those that water quality on the backside? And what we found was, yes, everything is going through our membranes except the PFAS. So as you're looking at that membrane system, we're getting a concentration of anodic ions on one side and the cathodic ions on the other. But the PFAS has been taken out. So now we know that if they have a problem with nitrate or arsenic, or you got a chloride issue, well, those can be dealt with in the side chambers before it's blended back together. So when you're looking at NEPS permits, this is where it can come in handy. So as you can see here, we were able to drop the conductivity, the chlorides, the hardness down. We did do future manganese testing, and we were able to remove the manganese. This was a case before we started using SGS as the lab, and they messed up the manganese testing. You'll notice that we don't change the conductivity much in this. That was something that we were able to blend everything back together so your conductivity stays, or your pH stays fairly normal, sorry. And that we were lowering the COD, which was something that surprised us as we were looking at our testing. So this is what a system looks like, and I don't want this to be a sales pitch, so I'm not going to really go through this, but I just wanted you guys to have it for the future. And also it's a great picture of what the system looks like for a remediation site. The modules, they're in the small circle. That's what a module looks like. So as you're looking at that, you've got your anode and your cathode, and you can kind of see where the water goes in, and then on the top, and then is pulled out of the chambers at the bottom. So it's a modularized system. So that means that when you hit the end of its usable lifespan, we needed to know what to do with it, because we didn't want to create mountains of waste. We didn't want to create a liability for people, and we had the luck of developing this very slowly. So being a small company, it was always do it as we had the money to do it. But that allowed us to watch other technologies being developed and figure out what were the most important things coming out of that. So one of the things that came out of that was that we were seeing these mountains of waste that were being produced by the traditional treatments. So we knew we had to go past that step to a destruction step. So what we do with our process is we're able to actually, we created a process where we take that membrane apart, or that system apart. We take those membranes out and we strip the active surface off of them. So what you see is the concentrate that's created after you strip the active surface out. So we could treat the same amount as 40,000 pounds of carbon, and we'd end up with that beaker of goo. And then we take that beaker of goo and we created a process using electrooxidation, which I can't show you yet because it's not fully patented. so they don't let me take it all out here. But it's a unique process that has a little higher energy density transfer. Higher energy transfer, the energy density is a little bit more, so it allows us to salt out the PFAS. One of the things that we noticed in this system as we were doing all of our testing is that because of the way the system works, the conductivity and the PFAS removal mimicked each other. So in our piloting, that allowed us to have an ability to watch PFAS removal in real time. But it also allowed us to know when those modules needed to be cleaned. So it really allowed us to push the envelope and see how far we could push those modules to know exactly how much removal we could get as we were doing our testing. So we were able to push them about 700 hours in between cleaning cycles. So as we started working on the process, we knew we needed to step beyond just clean water. Most water that we're dealing with PFAS is not going to be all that clean. We're going to run into surface water. Groundwater doesn't always come out clean. So we knew we needed to go beyond that just clean water. And so we started looking at things like secondary effluent from wastewater. And we started looking at leachate. And we found that we were able to deal with leachate in a treatment train very well. So this is actually leachate from Florida. I can't tell you where, but I can tell you it came from Florida. Their goal was 70 parts per trillion on the removal. And you can see that they came in at about somewhere between 1,000 and 2,000 on the PFOA, and that was really their contaminant of concern. And we were able to run it through our system using our treatment train, which was a combination of our AEC system mixed with a way to actually lower some of the COD on the front end. And with that, we were able to take their system down to the crazy low 1 part per trillion that everybody said wasn't possible on leachate. We were also able to deal with some of the other contaminants that you're going to see in the RECRA work, in the RECRA regulations that have been proposed. And we were able to take them all down to pretty low numbers. So this is what it looks like. We've since run a couple of other leachate trials. I apologize for the left to right instead of right to left on the beakers. So you can see what it looks like untreated, and then it goes through a series of steps, and post the AEC process, you're clear, and we've been able to, over the course of all of this, get over 99.9% removal of the PFAS from the leachate. Maybe not on the first set of trials, but overall, in the end, we've been able to do that. So this is raw leachate. That was post a UF process. So this one is actually raw leachate coming in. And you can see that it actually even performed better on the raw leachate than on the UF system. And then this one I want to spend a little time with because of the presentations that we've had. This is actually foamate from foam fractionation. So this we were actually able to take the foamate that had been brought down to the liquid again, and we were able to actually run that liquid and take it down to where we created a small beaker of goo, and then took that through a disposal process. And by doing that, then there was no circle liability left for that particular customer because it was all salted out PFAS. And you'll notice that in the when you're dealing with leachate, we're getting a lot more of those short chains. Where you can see that we can take them out, and we're getting a lot more of the ultra shorts as well. So that's kind of a summary of what you see with the leachate. Part of the reason that I always bring up leachate last is that we all know that the regulations are coming on our wastewater. on our leachate. And one of the things that happens is as we move towards those entities, traditional treatments struggle to work. And it forces us to look towards advances in our treatment technologies, because anybody that has worked with secondary effluent on a wastewater plant or worked with leachate knows that you're not going to stick an activated carbon system on the back end of a wastewater plant. You're going to burn up carbon too fast, and you'd end up creating mountains of it in a heartbeat. I just had contact from somebody, and we won't talk about which military base, but there was a military base that had a wastewater accident. They had a lagoon, and somebody decided to dump AFFF in it. And now it has to be treated. But rather than bring in a consultant that knew about PFAS and knew about wastewater, they just tried to go about it real quickly, and somebody decided to put an ion exchange system on that lagoon without any pretreatment. Anybody want to take a guess how long it took before it clogged? Yeah, it was like 10 minutes. So really, when you're looking at the treatments, really, I bring that up to encourage you to look at the type of water that you're dealing with. Not all water is the same. Not all water treatment is going to end up being the same. I think my cohorts would agree with me when I say that none of us fight against each other, because there's more than enough PFAS for all of us to treat. And so we all work together to find the best treatment for everybody, and sometimes that's combining the systems. Sometimes that's looking at one system over the other. I know I personally recommend my competitors multiple times in a day when it's something that doesn't fit my system. So just know what you're looking at when you're treating the water and what's in it, and look for the best treatment that's not going to, as I call it, kick the can down the road. So in conclusion, I think I've kind of talked about it. We don't produce a concentrated waste stream. Instead, we produce a low amount of waste that we then take and destroy. And it's a very low energy option. For as much as I talk about an anode and a cathode, I don't use any more energy than an RO system would, and in most cases, I'm much less. And if you need to find me, there's my contact information, or look for the gimpy girl that's walking around in a walking boot. And I'll take questions.
Sorry, I'm going to ask a lot of questions during this session.
That's what you're supposed to do.
Exactly. So 2 quick questions, and I actually have a lot more. I'll find you later. But is the membrane something that you created and it's patented, or is it like a commercially available membrane that your group was testing and you're like, hey, look at this?
It's a proprietary process. It's not a proprietary membrane, but the way we use it is different than a standard membrane.
And then the second question is, you said, I guess the membrane between cycles lasts about 700 hours.
Mm-hmm.
So for instance, if I'm using your process in Florida and I get to that 700th hour, how do I swap out my membranes? How do I get them back to you?
You don't, the membranes last 700 hours before cleaning cycles. So the system will go into an automatic cleaning cycle, but most systems will have multiple modules. So they'll go one module at a time. So you'll never really lose your flow. And then when you hit about 1 to 3 years, then we actually take the module back and we swap it out to you. So we come on site, all you see is a exchange.
So then and I apologize, I'm asking all these questions. So the destruction of the goo at the end, is that also performed in the process, or does that have to be?
No, it happens either off-site, or we bring a destruction process to site and take care of it there, whatever the customer wants. Okay. We don't, we can do it either way. Mm-hmm. But that PFAS is bound to that membrane, so it's got to go through a stripping process before we can actually go through the destruction process. We don't believe that, and this is just personal opinion, but we don't believe that you should do destruction in your stream, because if you do that, you don't know what you're making. Matter's never created nor destroyed, only changed. So you have to make sure that when you split that CF bond, that what you're getting on the backside isn't worse than what you started with. You promised me hard questions.
I did. I'm really just, perhaps this is a question for the panel, perhaps this is just a comment. As an industry, we together, all of us, we're facing this forever, everywhere chemical. We have to consider environmental policy. We're dealing with what the federal government wants to do, how the federal government wants to handle it. Obviously, if it's raining, that's a de minimis condition compared to an AFFF military base where it's a highly concentrated source, or obviously if you're working on the line and you're exposed to it, you have health impacts. Obviously, environmental policy needs to be centered around health impacts and toxicology and exposure and preventing people from getting sick. So with that kind of introduction and where we are with environmental policy, where do we stand in terms of municipalities, all the local governments that have to deal with this at the source, the water that comes into our tap? How are they doing, these municipalities, in terms of monitoring and treating what we're drinking?
So the Safe Drinking Water Act was published, and they gave municipalities 3 years to comply. The first year made them start testing everything that's in. So within the first year, all municipalities had to test using 537.1 on whether or not you had measurable PFAS in your water. Now that had two numbers. The first number was, are you over 4 parts per trillion on PFOS and PFOA, and then it was 10 parts per trillion on 3 of the 4 others that are included in the rule. The second number was, are you below half of that number? So it was 2 parts per trillion for the PFOS and PFOA and 5 parts per trillion. That was a testing indicator. If you were below those numbers, you only had to test once a year after that. If you were above that 2 or above that 5 on any of those, or above the hazard index half number, then you had to start testing quarterly to see if you're going to go above that treatment number. So they are taking a stance. Now, having said that, safe drinking water numbers are being challenged in court. We don't know what's going to come out of those numbers, but as they stand right now, that's where they sit. The bigger problem is, how are we going to pay for it all? And what's coming next? Because the EPA was never stopping at the 6 that we have for safe drinking water numbers right now. That was never their goal. Their goal was originally to go from 2 to 6 to 16 to 25 to 40 to all of them. Okay. That was their goal, but that becomes a very, very expensive goal to try and meet.
Okay, thank you. And this last question is just simply yes or no. Is and has the toxicology demonstrated 4 parts per trillion, in your opinion?
Toxicology has shown up at lower levels. If you really want a good indicator of how the toxicology affects people with, in the PFAS realm, watch the documentary on YouTube. It's called The Devil We Know. Don't go The Devil I Know, because you'll end up with very strange psychological, mind-bending. Go The Devil We Know, because it's the story of the health, it's the story of the PFAS lawsuit that was the second lawsuit, and that's that led to the medical monitoring claim.
To answer your question on municipality testing, so the UCMR program is ongoing, and they've been collecting data through various municipalities through the state organizations. So if EPA gave primacy to the state to regulate it, then they are going in and collecting samples and sending it to the labs, and then they'll do the statistics after the 3-year period of collection of data, and then based on that, the outcome may change on the regulatory limits. So that's what's going on under the UCMR program. Any other questions, folks? If not, we will go over the next presentation. The next presentation is 2024 PFAS regulatory update. Does it matter to phase 1, phase 2 site assessments? And that's being presented by Nicholas Albergo, professional engineer and senior advisor to GHT. Please welcome Mr. Nicholas Albergo.
Most of you'd argue that professional and Nick Albergo shouldn't go together. It's true. I spend most of my time now contaminating the minds of the next generation of engineers. I'm very good at it. It's true, I also am a senior advisor at GHD, where my job is to come to the office in the morning and turn on the lights to make it look like the place is open, since everybody else works from home now. I have a unique place here at FRC. I founded this conference 30 years ago, along with the publisher of, at that point, the Florida Specifier. His name was Mike Eastman. Those were some lean days initially. We paid speakers to come to try to bring in the crowds, and it was just me and Wilbur. No. I blame Wilbur for many things. One is I'm an alcoholic, and part of that's on me, but part of that's on him too, man. Just a show of hands, and once you put your hand up, just keep it up, just to give you an idea who early on the speakers. Anybody remember Jim Garrity, Garrity and Miller? Okay, keep your hand up. How about John Cherry? Dr. John Cherry out of University of Waterloo wrote the groundwater book, Freezing Sherry. Okay? How about George Pinder? Anybody remember him? He's the father of contaminant transport. Okay? He was a speaker here. Frank Rovers, he was the architect and designer of the remediation system for Love Canal, and he holds a very special place in my heart. He's the one that essentially bought my firm when I sold. But he was the first guy to get up and say, I used pump and treat and it sucks. Okay? And it didn't work, which was, a lot back then in the 90s. How about Jim Mercer? Cohen and Mercer, they were the Dean Apple guys. Okay, they wrote the book on that. So what I'm getting at is this conference has evolved over time, but its underpinnings, if you will, are on some pretty significant pioneers in the field. The fact that they allow me still to wander, largely irrelevant, with my incoherent ramblings to former students who really shouldn't be here. You've heard my bullshit before. To many former employees, it's great, but think about it. At the end of the day, I'm the only thing that is separating you from alcohol right now, okay? What was I gonna say? It's great not to care anymore. All right. So we're talking about PFAS. By the way, that title of my presentation, I ain't going to do that. So what's going on in PFAS? Well, it's out of control, man. I mean, these are some of the lawsuits that are out there right now. There are hundreds of lawsuits right now, okay? They're saying PFAS is in the bubble yum. Maybe that's why the Yankees lost, right? PFAS is in the tampons. PFAS is in the Hershey Kisses. These are the lawsuits that are out there, okay? But they're largely based on TOF, total organic fluorine analysis, which includes all the total fluorine, including the inorganic fluorine. And when you start to look at those totals, okay, there's a lot more of other stuff in it than there is organic fluorine. And so the typical defense to all these lawsuits is to say the regulations talk specifically in terms of numbers and in terms of which PFAS we're talking about, and you got nothing. And so a lot of them are going by the wayside pretty quickly, but they're coming and there's more to come, and that's important to keep in mind because it's not going to go away anytime soon as a result of that. You heard DeMaio this morning talk about this stuff, so I won't go over it again. Arguably, there's millions of PFAS compounds now if you consider the structural isomers and the salts and so forth. So it's a monster list. And what are we up to? Maybe we can analyze 41 of them now with 1630.
1633.
1633 is 41 out of, arguably millions of them. So I don't know what we're going to do with all that. This gives you an idea. If we just look at the documented cases of PFAS, and we just look at the obvious stuff, the airports, the landfills, wastewater treatment plants, okay, we already got 44,000 cases around the country. You want to add in another 700 with our DOD sites, you could throw them on there, but eventually I could fill the map, okay? So, as you heard, it's everywhere. It's not going away anytime soon. The other thing that's kind of interesting is we really haven't talked much about what's happening around the world, but we're not the new players here, okay? We're actually coming late to the party. What makes us new is that we're establishing levels that no other country's even considering, okay? So that's what is kind of different about the US versus what's happening in the rest of the world. They're looking at levels anywhere from 50 all the way up to 500, much more realistic levels, okay? So their approach is different. Now, part of the reason their approach is different is they don't have the money we got, right? So there's no way that they can handle it the same way. But the reality is, there's not going to be any quick fix to this stuff. There's this study that came out that said out of 101 different companies that produce bottled water, 40% of them have PFAS in the bottled water. Okay, so it's a problem that is going to take a very focused strategy, and we don't have one right now, and that's really a shame. But the reality is that we came out in 2021 with this strategic roadmap to try to push forth an agenda on PFAS. We kind of let it languish for almost 4 years. 2024 came along, and all of a sudden, EPA freaked out and passed more regulation than ever in the history of the agency itself. And this gives you an idea of just how many regulations have been passed in 2024. Okay, and whether we're talking about the Toxic Substances Act and the reporting, or the passage of the primary drinking water standards now, the RQ releases, changes to our consumer confidence reports. We added it to circular hazardous substance lists. We're threatening to add it now to our RCRA list. We're changing our industrial classifications in NPDES, which is going to be a huge deal with stormwater management. We're holding hostage our largest wastewater treatment plants and actually testing their influent, effluent, and biosolids. All right, so there's PFAS in the biosolids. Now what? Well, where are you going to put it, right? We should dump it on DC, where it belongs, right? So there's a lot going on. This last one's kind of interesting. They've held hostage 10 huge industries, and they're actually forcing them to evaluate how much different kinds of PFAS that they've got for the sole purpose of turning around and hanging them with their own data. So this is all 2024 stuff, basically, outside the NPDES. This has all happened within the last year. And the money's astronomical, right? I mean, they talked this morning, DeMille talked this morning about the election and so forth. I'm not sure Trump really cares about this stuff. He's got bigger fish. Unless the Mexicans are going to put PFAS on their back on their way back across the border, I don't really see it as a big deal. So I think we're going to have PFAS around for a while in terms of the regulations, and the money, we can't afford it. That's clear. We're not going to be able to afford it. But what I really wanted to talk to you about is some of the challenges that are coming up as a result. Not the technical, because you've been hearing all day about that. But I want to talk about some of the political challenges that are happening. And one is just the fact that the communication surrounding PFAS is a disaster, right? There's already uncertainty regarding how it occurs in the environment, how it cycles through the environment. I mean, even if we do this treatment you've been hearing about, what's to stop the end product from sneaking right back into the environment after we treat it, right? And we've got to do something with the concentrate and the filter media and all that. I don't know where this stuff is going, right? We have a lot of disinformation about cancer. And, you know, let's face it, the cancer fraternity has been pontificating for years about what causes cancer. And 1 in 3 of us are getting cancer anyhow. I don't know what 1 in a million excess risk means much when we talk about things anymore. It's very likely, I've said this before, that more people need to die. We're going to have to come off the 1 in a million excess cancer risk and look at maybe, I don't know, 100 people die out of a million instead of 1. I know that sounds rude, but that's why they allow me to wander, right? There is huge litigation going on right now. The big dogs are fighting. Okay, here's an example of the United States Chamber of Commerce is suing EPA right now over the Circulating Hazardous Substances designation. And what they're arguing, it's actually a very unique situation. EPA, in its effort to push regulation down our throats quickly in 2024, for the first time used a little known caveat of CERCLA section 102A that said, if you EPA believe there is substantial danger and exposure that you can shove through the regulatory process and circumvent some of the typical ways that regulations are promulgated. So EPA hung on this, and as a result, they passed the Circulating Hazardous Substances regulations, changing and putting in PFAS. But what the U.S. Chamber of Commerce is saying is, you never actually proved the whole issue of exposure and the danger associated with that. You just claimed it and used that as the vehicle to push through the regulation. You didn't do a cost-benefit analysis, which is supposed to be part of every regulation. You circumvented that. You never even put the rule out to peer review, which is traditionally done so that we don't wind up allowing junk science in through the back door. And then even on top of all that, there's the argument of whether or not CERCLA is the right vehicle for a diffuse anthropogenic pollution. I mean, think about it. CERCLA is all about identifying a source and a release, right? You got this facility, it dumped this shit in the backyard, and it needs to be cleaned up, right? But that's not how PFAS works, right? It's already everywhere. So who is the source? Who's the facility? And what are we going to do about the release? What release? It's on Mount Everest. It's raining in Miami, right, Wilbur? Wilbur doesn't like that at all. I know you didn't like that. It's raining PFAS in Miami. Anyhow, maybe I should go back to drinking. All right. Anyhow, so there's a lot going on in terms of challenging the rule itself from this angle of the way it was promulgated. At the same time this litigation's going on, the American Water Works Association is also suing EPA over the drinking water standards. And what they're doing is they're piling on the U.S. Chamber of Commerce, all those arguments, but they've added some of their own arguments, okay? And one is that they never looked at what the liability would be to the public utilities of forcing them to treat drinking water. Because what are you going to do with the filter, with the concentrate, right? If it's a hazardous substance, then you've turned every single water treatment plant into a freaking generator who is carrying circular liability into perpetuity wherever that crap goes. Okay, and it's like, what's the plan here? And then if you look at the longer term deal, they're saying that by 2029, not only do these drinking water utilities have to address the treatment of it, they've got to report to the public if they've got PFAS. Well, what do you, I mean, you might as well put a sign up for Morgan & Morgan, right? For the people. They might be busy with reefer by then, right? DUIs for reefer. But the idea is that a lot is going to happen as a result of pushing this kind of regulation on our utility system, on our municipal system. So at the same time, the circular regs are being challenged, so are the drinking water regs. And if that isn't bad enough, then EPA's also got an issue with its own TSCA reporting requirements. They had said that by now, we're supposed to be in a system right now where we're reporting PFAS. And take a look at the two things to the right, those, I don't know, what do you call those things? Those little pull downs, but it's not, I should have done it interactively with a pull down. But so one of the things is that they want everybody to report products that were imported all the way back from 2011 to 2022, that period of time, okay? And look at the last one. That includes PFAS where it was known to a reasonably ascertainable by the manufacturer imported, even if it wound up in there accidentally or in trace amounts. Now think of the logistic train that a lot of these larger companies have, the product logistics train. I don't even know how you figure out whether or not you've got PFAS and where it showed up and when it got in there. But think of the magnitude of data that generates. And as a result, EPA, after it passed the rule, has now backed off and said, oh man, we really didn't expect it was going to be this much data. And frankly, we're going to have technical difficulties digesting that data. And we don't have the budget to manage that data. So you know what, even though we got a rule, never mind that, we're going to delay it. And then, as you know, EPA came along and said, yeah, we got a circular rule about hazardous substances, but here's a memo that says, yeah, we're not going to enforce that. Okay, so you're already seeing the backtracking of enforcement and regulations. And I think you're going to see more of it until this all shakes out. What is a really interesting twist comes from the Chevron doctrine, which up until recently said, during litigation, if the judge is unable to really focus, the judge and jury can't really focus and understand the nature of the definitions of environmental concepts, okay, that they would defer to the agency. They'd bring somebody from EPA or DEP in, and that individual would explain to the court what is meant by X. And this is how we manage or enforce X, okay? And that made perfect sense. But what this lawsuit did was overturn the Chevron doctrine. And so now the judicial system has broad power to bring in whomever they want to interpret what is meant by definition. Now think about that. You got some federal judge, 85 years old, appointed to the bench for life by JFK, who's going to be making decisions about things like PFAS. Come on, okay? What it's going to do, it's going to create all sorts of interpretations of what's meant by our regulatory systems, enforcement, the mere definitions of things, what's in, what's out. And this is going to create even more problems than what we already have. And so this is all evolving at the same time. And of course, you've already heard, it affects everybody, right? It affects the consumers, it's going to affect how we regulate and how we enforce. DOT is going to have to come up to speed with how to get this stuff moving on the roads. What about our volunteer cleanup programs, right? Supposedly, you know, typically we have that pre-notification. Think about what we do for dry cleaning and for petroleum and so forth. How do you get into a program? You got to show you're contaminated, right? So are they going to go back and somehow, you know, look at PFAS? Because you're certainly going to find it. Think about dry cleaning as an example, right? We're going to find PFAS at dry cleaner sites. not because the PFAS is in the damn, perk. It's going to be there because the clothes had the PFAS, right? So how do we manage that? It's there, but it's not the release. We go back to, was it a circular release of a hazardous substance? No, it was the result of the methods that were being used. I don't know what we're going to do about groundwater. We're going to treat it as drinking water. That's going to be a disaster. I don't know what we're going to do with our biosolids from the wastewater treatment plants. I don't know what we're going to do with the sediments from stormwater management, okay? So there is such an effect, a roll-down effect of where we are in this, time frame with regulation and enforcement, that we need to take a step back, and we need to be more practical in our approach. And it's true. This is the best slide I could find on treatment technologies, some of which you've heard about. Okay, and it's true. We've got there's a lot of different ways to go about with treatment of PFAS. My challenge is we don't have anything that gets it back down to its elemental units, right? We can manage it and we can push it around, but chemically and biologically, we're not going to be able to get it down to the element form. And that's going to be a problem for us because it's almost like the hydrologic cycle, right? The PFAS is going to be somewhere in the cycle and it's going to just wind up getting back in to the environment in some other way, unless we go with some really fancy emerging technologies that, you burn it up or whatever. But I don't know if we can do that on a larger scale. We can do it at the university at bench scale, but to try to crank it up to what, the society might need if we're going to actually try to do something, I think that's going to be tricky. And so, as I mentioned, one of the issues is going to be the recycling of this stuff and whether or not we can actually get it out and keep it out. And the bottom line is whether we do the more practical approaches of filtering and whether we do it in situ, in the ground, reactive walls or whatever, or we do it by pulling it out, we're still going to be left with a challenge in that we've got a PFAS waste. So all we did was move it, rob Peter to pay Paul. And we're still going to have to deal with it. Yeah, there's new technology, super cool stuff. None of it's going to scale up to what we need. So it's great to get a Ph.D. dissertation. Zeke, you're going to do one, right? You're going to do one. Okay. When Zeke first worked for me, all he could say was, yes. Do you remember when I took you out and we got drunk? And you got all red. Why do Asians get all red when they drink? It's a weird thing. All right, so anyhow, to kind of finish things up because I wander otherwise, the bottom line is I think that what's going to happen with PFAS before we have another, a year from now or we do this all again, is we have to think about how broadly it's distributed and what we can realistically do to protect human health, which goes right to your point. And really, realistically, what we can do to protect human health is we can treat it at the source where we get our water from, because we're pulling it out of the ground anyhow, or out of a surface water, and we can certainly add some element to the treatment train to be more protective of human health. I think we can do that much. Outside of that, if we seriously want to talk about treating groundwater or soil or sediments or surface water, any of this other stuff, then I think, honestly, we're going to have to do a much better job of collecting the information we have, reviewing it, synthesizing what we can out of it, and that means we need a lot more workshops, we need a lot more engagement of the industry into the solution. We've got to do something about our messaging right now. EPA doesn't know what the message is, and the message that the public's getting is all over the place. So we need a stronger message, and as a result of that, maybe we can start looking at, other types of effective ways to treat other media. But I think that that's where we're at. Thank you. It's just thank you.
Thank you, Nicholas. Any questions from Mr. Nicholas? Yeah. There's one on there.
How does this relate to reporting phase ones for PFAS?
What?
Do I need to report it?
Hell no. Yeah, look, think about benzoate pyrene. It's a hazardous substance. Do you report benzoate?
Please use the mic.
Everywhere on your phase ones? No.
No.
No, you don't, right? So the fact that we added. What's that? Oh, why do I have to use? I had 11 kids. I can speak loud enough. Hello. Is it working? Okay.
Yeah.
All right. We added PFAS to phase ones because it's now a circular hazardous substance, right? But that doesn't mean you got to have a comment or opine on every single circular hazardous substance. If so, you'd already be talking about benzoate pyrene, and you don't. Okay? It's also a diffuse anthropogenic pollution, right? So here's the deal with phase ones, because it's circular driven. First and foremost, you got to have a facility. You have to have a source that you can look at, that you can identify, and that you can confirm that's where the schmutz came from. Then you got to have a release to the environment at that facility, okay? So the reason you don't need to freak out about PFAS is because if it's a diffuse anthropogenic pollution, then you did not have a release from a facility. Now, if you happen to be doing a phase one at the 3M plant, okay, and they had a pond where they discharged their wastewater, now you got a facility, okay, that discharged to the environment at the site. Now you got a wreck. Now you can talk about your PFAS, okay? But we're not going to go to a 7-Eleven that we are doing a phase one on and gratuitously throw it out there that there could be PFAS. Why? Because you don't have a release to the environment from a source. I would argue the same thing. Again, the issue with dry cleaners is that the PFAS is there because it came from the clothes, not from a release to the environment from an operation. And so, although I agree that there's PFAS there, well, first of all, if the PFAS is there, so is the perc. So we already got the wreck because of the perchloroethylene, probably, right? It'd be an unusual scenario where we're arguing that, yeah, we don't have a perchloroethylene release, but we think there's PFAS release. Because they got to go hand in hand. They had to have, right? And so, again, I don't see why we would separate PFAS out and treat it any differently than we would any other circular hazardous substance if it doesn't fall into the rubric of, do you have a facility? Has there been a circular release, a circular defined release to the environment that would be subject to regulatory enforcement if brought to the attention of the regulatory agency, right? Because if we could have a release, but it could be de minimis by definition. So all those things have to happen. I don't see any benefit in us gratuitously throwing out in reports PFAS. I think it's a red herring, especially when we have no standards. Right? I mean, we're still arguing about what, we got guidance concentrations. We haven't even formalized the guidance concentrations yet. So I'm a big proponent of not stirring that hornet's nest unnecessarily.
Agreed. Thank you, Nick, for your colorful...
See, there's somebody that agrees. Wilbur, tell us what you think.
Well,
amuse me.
Nick, thank you for your colorful presentation and perspective. I agree with your perspective. I agree we need to take a look back. I wanted to ask your opinion on my question earlier, do you think the toxicology supports the levels we're seeing out of the EPA? Has the science of toxicology demonstrated 4 parts per trillion?
That requires a more extended answer, but let me give you the crib notes. First and foremost, what's been happening is we've been trying to make the argument that there is a mixture effect, that there's an additive effect by different PFASs and their cancer-causing agents that becomes additive. And that's how EPA got around and used the CERCLA rules against themselves, okay? That part really isn't been well established, this whole idea that there's an additive effect. The challenge of trying to understand impacts at 4 parts per trillion is overshadowed by so many other factors that go into why we get cancer anyway. And I would say that that's the biggest challenge we have. If 1 in 3 and 1 in 4 of us are getting cancer anyhow, where do we find the population to evaluate at 4 parts per trillion without due consideration for all the other issues that are causing cancer in the world?
Will ASTM be coming up with any new documents in the near future on this matter?
Well, first of all, you can't use the word ASTM and near future in the same sentence. ASTM works at a geological scale. Okay?
Understood and agreed.
Right? So if you mean like 100,000 years, then yes, maybe. No, what ASTM is doing is they are not tackling, if you're asking about PFAS specifically, they're not tackling PFAS specifically. However, there are a number of standards that are coming out. Mostly standard guides, not standard practices. Keep in mind with ASTM, a standard practice is a you shall document. We're not coming up with you shall documents for PFAS. What we're coming up with is you should, which is a standard guide document, and it's addressing different elements where this could come into place. The most recent will be, the one you're going to see fairly soon, is going to be, again, on phase 1s, but it's associated with the continuing obligations, the way that you can maintain a CERCLA defense once you've established it through the phase 1.
Okay.
Thank you.
That's all the time we have for the questions. So if you have any questions for our panel members, they'll be around. And please have your discussions with them after this.
And real quickly, reception is going to be in the exhibit hall. Don't forget, we've got the 50-50 raffle, so applause for our panel.
Thank you. Thank you for attending the session.
And you can see why I put Albergo last.
Good choice, Dan.
Nice work today.
Right back at you.
Thank you very much.
It's always a pleasure hanging out with you guys.